So hello, now I will talk about the second exercise, task. It is about logistic regression and gradient descent on iris dataset. So initially we load the dataset as it was shown in our lessons. We divide the dataset into training and testing subsets by 80 and the 20%. So here is our logistic regression function for binary classification, which takes input data and their labels. This n represents number of features. So actually it is d plus 1, so it is 4 plus 1, 5 here. We create an empty weight vector, we initialize it, we randomly initialize it. This is the main thing. 2000 iterations there are, and eta is step size equal to 0.001. And wt, it is a matrix, empty matrix at this moment to store all 2000 weight vector values. Weight vectors actually. So in each iteration we randomly pick a sample from the training data set. Then what we do here is that we augment the data just to do a inner product when we calculate the gradient. So here is the formula of the logistic of the gradient for in the logistic regression. And this part, these brackets, the term inside brackets, it is the sigmoid function. So, this is where we update our weight vector. We multiply the gradient by eta and we add it to our current data weight vector. Then we store each weight vector into this matrix. So in each iteration there will be a weight vector. We store it into this matrix. So the function returns a matrix of the size 2000 by 5, so vectors. So we will use this function in this part where we are performing one versus all classification. There are 3 classes in the iris dataset, 3 types of leaves, 3 types of flowers. The first 0, class 2, class 1, and class 2. So 3 classes are there. So for each of the classes we do one versus all classification. Therefore we need 3 weight vectors, 3 matrices, 3 matrices that store 2000 by 2000 weight vectors. So we do the similar thing for we create a 2D matrix with 3 OVA variables or OVA labels. So 3 by 120, and for the testing labels we create 3 by 30 matrix, 2D matrix. So in here the value of k will represent the label in the iris dataset. It can be either 1, it can be either 0, 1, or 2, and depending on the value of k we will define the labels -1 or 1 in 3 ways. So the 1 in the first iteration of k will represent 0 class, in the second it will represent the second class, and in the third iteration it will represent the third class. So we label the same all data samples in 3 ways, but the training not labels but training features are the same, they don't change. So we feed it to the logistic regression function, we obtain wk, it is a matrix, a weight matrix we can say. So we calculate the in-sample error in a ways that for each iteration we pick a weight vector from our weight matrix here, and we check how it works for all training data sample, for 120 data samples in the training data set. So what we do here is that this part corresponds to calculating the score, like G, for the for the 0 class here, for the first class, for the second class. Each of them correspond to OVA. So what we do next here, we make this kind of an array where the index 0 corresponds to the first 0th class, index 1 corresponds to second, index 2 corresponds to this third class, like G2. Therefore we are interested in finding the index of the maximum term here, and this index will represent our label. So the output the values of G can take either 0 or 1 or 2, and we check if these values they are the same with the training labels. If they are not the same, we increment this variable train G, after which, after iterating through all data, we store it in the in sample error variable by dividing 120 just for the normalization. Then we plot it here. We obtain these types of plots where it decreases as the number of iteration increases. In the beginning, the error is quite high, but as it goes, it decreases to almost like 10% by the 2000th iteration. So you can see it's gradually decreased and it fluctuates along the way. So what we do here is that we do the same calculation for the test data sets right now. We change the 120 to 30 here, and we training set we change it to test set, and we do the same operation here. When we plot it, we obtain this kind of plots. It's also a decreasing plot. It kind of corresponds to the peaks and falls of the train in sample error, but as you can see, it's more like there are more flat horizontal lines. It's because that the out of sample error is the same for several iterations, because there are only 30 samples, and these 30 samples can be successfully divided, like equally divided by several iterations in a row. So that's why there are a lot of horizontal lines, but in general it decreases to sometimes even lower value than in sample error. So just to check it one more time, let's run it. It will take some time, but also the plot will not be exactly the same, but will be similar because we randomly initialize the values of the weight vector in the beginning. So yes, this is the training data, training in sample error plot. Here we have a normalized out of sample error plot. As again, they are quite similar. They decrease along the way, and the reason I think that the out of sample error is kind of small here is that there are only 30 samples, while in the training data there are 120 data samples. Well, this is I think why this is I believe why it has a lower value than the in sample training in sample error. So this is how it turned out to work. Thank you for your attention.